Bonjour à toutes et à tous. Un grand merci pour votre présence. Nous avons le plaisir aujourd'hui d'accueillir le docteur Geoff Appelboom. Donc, docteur, vous êtes neurochirurgien et chercheur au centre médical de l'université de Columbia, New York. Donc, vous venez exprès de New York pour nous faire cette conférence dont la thématique sera le cerveau, dernière frontière de la digitalisation humaine.
Parfait. Merci beaucoup, Yann. So I'm going to do the talk in English. Thank you so much for inviting me. It's really a pleasure to be here. I was here last year, and I thought the quality of the talks and the people here was really amazing. So I'm really happy to be here and present this talk. So we were discussing about what kind of subject we could talk about. I thought that this was an interesting subject because it could link what the conference was about, which is really about digitalization and how we create data from what we observe in the human body, and try to link that with the brain, which is a little bit more what I know and I'm comfortable with. And so I think that it's a definitely interesting subject. I'm going to talk about how there is a movement right now to digitalize human bodies, and how the brain is really trying to keep up, but it's a very complex organ, and there's a lot to be learned with it. So I'd like to start with talking a little bit about personalization. I think it's something that you guys have been talking about for the past 2 days now, and I think it's a very important concept. Personalization is really the idea that all of these people, all of us are different, and that we should not treat everyone in the same way. There are a lot of differences at a lot of different layers. And if you look at the way people think about it, around 10 and 15 years ago, people were really thinking about the fact that DNA was everything. That if you look at the genome, you can predict all the diseases and everything that's going to happen in the rest of your life. But things have changed, and now people are thinking a little bit differently. Is really DNA the only thing that matters? And now we're even moving towards another kind of concept, which is mapping our differences. How are we different, and how these differences will affect all of us, the treatment strategies, the intervention, the monitoring, etc. So, to me, what makes us human is a mix of different things. And I think that if you look at the genome, is one part of it, but there are multiple layers. These layers are getting more and more complex. But you have the genome, then you have the proteins, then you have the microbes in your gut. But you also have what you look at, the organs as a whole, as a microscopic entity. But you also have all the physiology, all the parameters that you see on a daily basis, all the changes that you see in your blood pressure, in your glucose. That's the physiology of your human body, also called physiome. And then you have your social graph. So if you look at all these layers will add up and make us very complex and very different human beings. And I think what the challenge is that all these differences have different applications, and all the people that have to come into play to be able to map these differences and make them understandable have different skills. 20 years ago, 50 years ago, biologists were really important in medicine. Now we realize that engineers, computer scientists, physicists have a role to play as well, and we don't speak the same language. We don't have the same mentality, and we don't work the same way. So how can we talk to each other? How can we work together? This is a really important question. And if we don't talk the same language, if we don't know how to interact with one another, how can we define new strategies? So I think that in order to be able to map our differences, we need to be able to come up with a common language. And this common language will help us understand our differences and will help us change from that pattern of one fits all to one doesn't fit all, and we all can be different in terms of surveillance and data, in terms of testing, in terms of treatment strategies, and in terms of our intervention. So that's the reason why I wanted to tell you about the digital humans. So this is a really a big movement that we see here that we've been talking about around the quantified self, and all these devices that help transform what we observe into digital information. And it's not isolated. If you look at all the disease and most of the chronic diseases in the US, you see obesity, around 80 million people in the US have obesity. If you look at sleep disorder, if you look at asthma, COPD, you see that already we have the tools at our disposal to be able to monitor parameters around the disease. And we are able now to quantify these parameters outside of the hospital. And this is a very important fact, because if you think about it, we could only assess 1% of the patient history, the only history that was in the hospital. Now we can look at the patient as a whole in a real-world environment, and we can understand how this patient responds to his ecosystem. And you see that, again, if you look at heart failure, you can already measure blood pressure almost 24/7. You can measure body weight, and you can measure medication compliance. So there's so many ways now that we can look at the disease from the initial diagnosis to the evolution of the patient. And this is a concept that you guys have been talking about for a couple of days now, but this is it really goes all the way through, from a sensor that you wear on your wrist to a lens that you have that you can put on your eyes that measure glucose chronically, that Google is developing. You have also sensors that you can ingest to track compliance with medication. So you're really understanding the entire patient experience in a new way. When you understand patient experience, you can also transform that into a change in behavior for the patient, called also biofeedback. So if the patient understands what will increase his blood pressure, he can try to avoid it in the future. So we're starting also to understand that the signal, being able to transform that signal, that observation into a actionable information, is definitely useful, not only for the doctor, but for also the patient himself. And so we see that revolution, and we've been seeing that revolution for 10 years now. But how about the brain? The brain is a well-oiled machine. It's a very complex machine, as you all know it. And it means that you need to account for 100 billion neurons. You need to account for 1 trillion synaptic connection. And we're still trying to figure out actually what most of the brain do. Only 1% participate in memory, but most of 80 or 95% actually of the brain is something that has an action that we don't really understand. And so if you think about it, there's around 70,000 thoughts. They travel around 500 kilometers an hour. So it's an extremely complex organ and system with an extremely fast processing information. And very recently, so in 2015, if you look at an initiative actually in the Silicon Valley, they took thousands of computers to create a supercomputer, and they only tried to simulate 1 second of human activity, 1 second. It took them, with thousands of computers, around 1 hour to be able to simulate only 1 second. So you can imagine the complexity to be able to understand that brain activity and be able to replicate it. What's complex about the brain as well is the fact that there's two things. One is there is the anatomic construction of the brain. So everybody's familiar with the frontal lobe, the temporal lobe, the parietal lobe, but these are only anatomic differentiations of the brain. The problem is that there's also functional aspects of the brain. So parts of the brain have different functions. Sometimes they are located in different parts of the brain. That makes it very, very complex. Right now, at our disposal, we have mostly anatomical tools that help us just navigate into the anatomy of the brain. To make an analogy, so this is a diffusion Mri. And to make an illusion, it's like the Google map of the brain. So this will tell you where are the highways, where are the roads in your brain, but we have no idea where they lead to and what's their function. We know most of it, but we don't know all of them. So we have a good idea of how the brain is structured. We have a good idea of all these roads and highways, but we don't really know what they do. We don't know where the shops are. We don't know where the restaurants are, where the movie theaters are. So it's it's extremely complex. But if you only look at the roads, you can already differentiate men and women. So the connection between the right and left brain of men and women are different. And women have more connection between the right and left brain. That's probably why they can multitask more often and are better at it. But men, for example, have more connection between the hemisphere of the cerebellum, which probably means that they have an easier way to do tasks and learn new skills. So that's for anatomy. But if you think about functional, it's another story. So to be able to understand functional, multiple approaches have been undertaken. And one of it is using the functional MRI. And I won't go in details, but really the idea is to test a person, a patient, and see how his brain reacts. And what his brain reacts means that we're going to look at the oxygen in the brain in different regions to understand what part of the brain will be activated with a stimuli. So for example, we show a face of a patient to a patient, and we look at the regions of the brain that will be activated. And this is a way that we've been mapping more and more the brain with more and more complex tasks. That really helps us combine the anatomical differentiation of the brain that we know and the functional one, and combine it. So to make an illusion, it's like we have the Google map of the brain. Now we have also, we know where the light is turned on in different parts of the brain. So we know that in the brain, people drove their car, stopped there, opened the light, and that's a restaurant probably. So we're trying to understand these things. And the third part, I think, that really combines our understanding of the brain is really the electrical activity. And everybody is familiar with the EEG, and so we understand that concept of brain activity in terms of electricity. But most people are talking more and more about it as noise. We don't really know what it means. It's extremely complex. And one allusion we can make is to say that it's almost the equivalent of hearing noises on the highway and being able to understand and trying to figure out what happens. There is high traffic that we understand, but what does it mean? So the complexity of the brain is that you need to integrate all these different things together, and it becomes very, very complex. There's a lot of different companies, from medical to also in the quantified self movement, directly to consumer, that have been trying to tackle this problem, and they are focusing mostly on electric signaling to be able, for example, to try to relax you, to try to control your emotions by understanding how the brain signal and the electrical signal changes. But I think what is the most exciting for us as neurosurgeon, but also for patients, is really to be able to deep sense now. So we can introduce electrodes in the brain at different level, and that actually helps us understand also the electrical activity of some regions of the brain. And 2 or 3 examples of that is really now the change in the paradigm of treatment of patients with Parkinson's disease, for example, where we now can implant electrode and stimulate with an electric signal deep in the brain, and these patients actually are sometimes symptom-free. And I want to finish with this video. I don't know if you're familiar with it, but it's a very famous violinist in the US that had all of a sudden an essential tremor, so couldn't play, was about to give up his job, and was one of the first, actually was the first to receive an implantation of an electrode to be able to overcome his symptoms. The patient needs to be awake because we need to be able to understand if the stimulation will help him and will not hurt part of his system. So this is the OR. You see that they're implanting the electrode in the patient's brain. And you will see also how the patient reacts during the operation. You see directly that there is a change in the way he plays. So you have sensor on the entire violin, so you can really see the pattern of movement, the sensation the patient has as well. And you see that you can record with the electrode also the electrical signal inside the brain. So we will see the patient, this is the patient being stimulated, so you see that the movement is more fluid, the patient is extremely comfortable, so he has an electrode in the brain, but he's happy about it. And you see more and more these techniques that will definitely change the way we perceive the brain. So just to finish with that, we'll see the patient being able to turn on and turn off the pacemaker that he has. So this is the patient afterwards. He tells a story. So this is with the pacemaker on. So you see the patient extremely comfortable. You don't see anything. But you will see that he has a small connector that he can turn on and off, and that will affect the fluidity of his movement. So he just press a button like this, and all of a sudden he comes back to the old self. And you see how hard it is for him to be able to play the violin. So here it is. I wanted just to show you and briefly introduce the brain, the complexity of the brain, and to tell you that more and more understanding of the brain, the way it functions, and the ability for us to be able to transform everything that we see into information and signal will help all the community, the doctors, the engineers, the computer scientists to find new ways of treatment. It's already there and it's very exciting. Thank you very much.